Okay, let's just dive right into this, shall we? Welcome to This Explainer. Today, we're going to uncover the hidden patterns of relationships that drive modern computer science. We'll be pulling our insights directly from Amon's AI journal, specifically focusing on the distilled wisdom surrounding LeetCode graph problems. You know, if you've ever felt completely overwhelmed by abstract data structures, you are absolutely in the right place. We're going to decode them together.
I want you to think about this for a second. How do you find a secret judge hidden within a crowded town? Or, better yet, what do a secret town judge, a central star network, and a complex maze all have in common? On the surface, I know, they sound like riddles from some old mystery novel. But underneath, they are all elegant expressions of the exact same mathematical concept. To figure out how they connect, we're going to act as algorithmic detectives today. We'll be hitting 5 main beats: the pattern of graphs, center of a star graph, unmasking the town judge, finding valid paths, and finally, mapping all possible paths. Let's get to it. Section 1, the pattern of graphs, nodes, edges, and logic. Welcome to a world where literally everything is a connection just waiting to be mapped out. But before we get into the heavy code logic, we really need to ground ourselves. Graphs are fundamentally about relationships. You have nodes, which represent entities, right, like people or cities or web pages, and you have edges, which are the lines connecting them. By framing these algorithms as ways to uncover hidden relationships or navigate complex webs, we can make the actual code incredibly tangible. You aren't just traversing an array, you are mapping a living network. All right, case 1, center of a star graph. This is based on LeetCode 1791. So what exactly are we looking at here? Well, a star graph is an undirected graph with exactly one center node. And that center is connected to every single other node by exactly n-1 edges. Think of it like a bicycle wheel with spokes connecting to a single central hub. Because it's undirected, traffic flows both ways. But that central hub is incredibly unique. It's literally the only node in the entire structure with more than one edge. Now, for this first mystery, we are absolutely looking for maximum efficiency over brute force. If you were to tackle this using a generalized approach, say looking for multiple centers in a multi-star graph, you'd have to search the whole graph. That would give you a time complexity of O of n. But instead of searching the whole generalized graph and eating up that O of n time, our source reveals a brilliant shortcut specifically for this single-star problem, and it drops our time and space complexity all the way down to O of 1. So here's the real kicker. Any 2 edges in this graph absolutely must share a common node. And that common node has to be the center. You don't need to traverse 100,000 edges. No way. You literally just check the first 2 edges provided in the input, identify the one overlapping node between them, and instantly return it. It is an algorithmic masterpiece of efficiency. Moving right along to case 2, unmasking the town judge. This one comes from LeetCode 997. Let's escalate our detective work a bit to directed graphs, where trust only flows one way. Picture this scenario. We've got n people in a town, labeled 1 to n. The rules are super strict. If a town judge exists, they trust absolutely nobody, period. However, everybody else in town trusts the judge. We're given an array where each entry shows that person A trusts person B. From this massive web of one-way trust, we need to find the one single entity who hoards all the trust but gives absolutely none away. This brilliantly illustrates how we can untangle a complex social web simply by keeping a running score for each person. Here's the elegant logic behind it. We create a score array. If a person trusts someone else, we subtract 1 from their score, because remember, the judge trusts no one. If a person is trusted by someone, we add 1 to their score. After processing all the relationships, the true town judge will be the only person left standing with a score of exactly n-1. And because we really only need to track this basic integer trust score for our candidates, our space complexity stays incredibly lean. As noted in Amon's AI journal, the space complexity is a beautiful O of 1. The time complexity is simply O of n, because we just have to pass through the array of relationships once. Boom. We found our judge without needing to build a massive memory-heavy matrix. Next up, case 3, finding valid paths, based on LeetCode 1971. For our third challenge, we're moving from identifying specific nodes to actually navigating the edges themselves. The core question here is wonderfully simple. Can you get from point A to point B without hitting a dead end? We have a graph with n vertices, bidirectional edges, meaning you can travel back and forth, and we're given a starting source and a final destination. We just need to return true if a path exists, or false if it doesn't. The constraints tell us right away there are no duplicate edges and no self-edges allowed. So to solve this, our source recommends deploying a depth-first search, or DFS. By using DFS, we methodically explore down a single path as far as possible before backtracking. What's super fascinating here is the complexity breakdown. The time complexity is O of n, but the journal breaks down the space complexity beautifully. It accounts for the graph, the visited nodes, and the call stack, which is O of 2n plus n plus n, which ultimately simplifies down to a clean O of n space complexity. We just systematically check paths until we either hit our destination or completely run out of roads.
All right, final challenge. Case 4, mapping all possible paths. This is from LeetCode 797.
Let's see how all this builds into an even more demanding challenge. To understand this one, we first need to define our environment, a directed acyclic graph, commonly known as a DAG. This is a graph with one-way connections where you can never loop back to your starting point. There are absolutely no self-loops, period. In this scenario, we aren't just looking to see if a path exists. No, our mission is to find every single possible path from node 0 all the way to node n-1 and return them all.
We're relying on that depth-first search approach again. But here's the catch Eamon's journal points out. If a problem just asks for the number of paths, you could use DFS with memoization to save time. But because this prompt actually asks us to generate and return all the actual paths, standard memorization doesn't really save us much time here. Instead, the solution points to an incredibly elegant recursive one-liner to generate these paths.
Now, what is absolutely crucial to understand here is the sheer scale of the worst-case scenario. That recursive one-liner gives us a brilliant, clean O of n time and O of 1 space complexity on paper for the algorithm itself. But remember, the worst-case scenario for the sheer volume of path variations, that can balloon exponentially. The journal illustrates this perfectly. Imagine node I is linked to node j whenever I is less than j. The total number of paths becomes roughly O of 2 to the power of n. So while your code is efficient, the output it has to generate can be massive.
Okay, let's pull all of this together. Here is your ultimate algorithmic cheat sheet from today's explainer. Just look at the progression we've made. We started with O of 1 overlapping edges in a star graph. We moved to O of n time but O of 1 space by keeping a brilliant trust score array for the town judge. We navigated bidirectional roads with DFS. And finally, we unleashed DFS recursion to map all possible paths in a DAG. This perfectly proves that mastering graphs isn't about memorizing syntax. It is entirely about recognizing the underlying patterns of relationships.
Which brings us to the end of our investigation today. As we close out this explainer, I really want to leave you with a provocative thought to ponder. Graph algorithms aren't just confined to LeetCode windows. They define social media algorithms, GPS navigation, and even global supply chains. So, if all human interaction can be modeled as a graph, what pattern are you? Are you a central hub in a star graph? Or are you quietly navigating a directed path? Keep looking for those connections. Keep analyzing the patterns. And I will see you in the next explainer.